Okay, so I'll walk through this one and see if you got all the parts, but I want to point out what these are. Again, this is individual concepts that I tried to separate out. They're now all part of the same thing. That's only happen if it's ionic. So when it's ionic, the first thing you do is you break it into its positive and negative ions. Then you decide if either ion is acidic when it interacts with water. So in practice one of the examples was ammonium nitrate. Nitrate is a pH neutral ion, but ammonium is not. And so ammonium, which is a cation, okay, it has an extra hydrogen. It's ammonia with an extra hydrogen. That makes it a weak acid cation. So if we decide something is a weak acid, then we then need to take the ion and write it as a weak acid. So anything that's an acid, you would write its formula. Dissociating with water. And it's weak, so we're going to do the equilibrium. And so an acid donates a hydrogen. And so ammonium without a hydrogen would be ammonia, which is its conjugate base. And the hydrogen transfers to water. The second part of what happens to an acid in water is it forms hydronium. So all weak acids, whether they're an ion or not, they will be in equilibrium with its conjugate base. So you got to remove a hydrogen and give it to water. So conjugate base and hydronium are the products. This is a equilibrium situation. And so there will be an equilibrium expression. So now that we have the reaction written out about what's happening, we're going to write the expression, but we have to make sure that we use the right K. So it's important that you label something as an acid so that hopefully that can remind you that the constant will be called a Ka. So you need to be sure that you write Ka because that is the acid behavior of ammonium, not the reaction or anything, just the acid behavior. And it's going to be, expression is going to be equal to the products, which is its conjugate base and hydronium, over the weak acid. So step one of the way that I go over equilibrium is write out the reaction, which we have to make up because this is a dissociation in water. Step two is to write the expression. And then step three is organize all the equilibrium data. So the equilibrium data is the constant and the equilibrium amounts. So the chart helps you organize the amounts, and then we have to look up or calculate the constant off to the side. So all of the tables are going to look the same if it's weak. So you're going to start by putting the concentration underneath your ion. It's a 1-to-1 ratio, and so that is the concentration of the ammonium. And we don't have any ammonia or hydronium to start with. And X amount dissociates to create X amount of ammonia and X amount of hydronium. So at equilibrium, there's 1.5 minus X, X, and X. So that goes here. X times X over initial concentration minus X. Okay. And that will be equal to the Ka. So because this is an ion, we're going to have to calculate the constant using the conjugate acid-base formula. So that is the conjugates. This constant times this constant equals Kw. So this is an acid, so it has a Ka. So ammonia will have a Kb. And that will equal 1 times 10 to the negative 14. So you find Kas in the weak acid chart, which is Appendix H. You find Kbs in the weak base chart, which is Appendix I. Our appendix for weak bases only has 5 molecules in it, and ammonia is one of them. Ammonium is not in the Ka chart. There are no positive ions in the Ka chart. And so we have to look in Appendix I and find Kb for ammonia, the very first one in Appendix I. It is 1.8 times 10 to the negative 5. 1.8 times 10 to the negative 5. So the math is the same for this little side calculation. It's always the constant for water divided by the constant that you looked up is equal to the constant that you actually want for this problem. And so it'll be 1 EE negative 14 divided by 1.8 EE negative 5. And so it's 5.6 times 10 to the negative 10. And so we calculated it. And again, this is not an expression. This is just a constant. So we calculated it using our Ka times Kb formula. So 5.6 times 10 to the negative 10 is equal to x times x over 1.5 minus x. So this is what I call step 3. And then it's just do the math. So once you begin the math, then you can look at, before you start, if you want to, you can decide if you can take a shortcut. And so our constant is very small, which means that x is going to be very small. So because this is so small, we can, in the math part, ignore the minus x because it's going to be such a small number that when you subtract it from 1.5, and then you round it for significant figures, it's not going to make a difference. Therefore, it's not going to make a difference in our answer either. So I recommend that you do this, that you go ahead and put minus x, and then you cross out just so that this reminds you of what you can cancel. You cannot cancel every x you see. You can only do the minus or plus x when there's an initial concentration. And you can't always do it. So you can't automatically ignore it. Okay, so now our math is going to be easy because it's going to be just constant times the concentration is equal to x squared. Which is 8.4 times 10 to the negative 10 is equal to x squared. And so x is the square root . 2.9 times 10 to the negative 5, and that's x. And x, for all of these acid-base dissociation, x is the value we want because it's going to be hydronium for acids and it's going to be hydroxide for bases. And so this is the concentration of hydronium. Which we will use to find the pH.